Howdy and welcome back. So we're going to begin implementing a doubly linked list iterator. We're going to do this as a class template. And I'm going to go ahead and point out before we begin that we could have named this something differently. I chose the name doubly linked list iterator because I thought it was descriptive of the type of, for the type that we're creating or defining or implementing. We're going to see that some changes will have to be made to our doubly linked list type in order for it to use the doubly linked list iterator type created here. But that's the next video. So let's go ahead and talk about implementing a doubly linked list iterator. So we're going to do this as a class template. The reason being is that a doubly linked list is also a class template, and therefore it can hold links of nodes for any type T, provided that they support the operations of the behaviors defined for that type. So because we could be dealing with nodes of different types, our iterator is also going to be defined as a class template, and we'll see why. Well, I guess we could see why now, because it is going to hold as its single data member a pointer to a node of type T. Okay, so that's left open at this point. When this is instantiated, that T will become a concrete type, and we'll have a doubly linked list iterator instantiated for a specific type. So just running through this, we can say, yes, indeed, this is a class template. The class name is doubly linked list iterator. And notice here I've included some inheritance. We're publicly including from some sort of standard library iterator type that has a couple of parameters here. I'm going to go ahead and say, or I guess comment on one and kind of leave it at this. The first argument to the standard library iterator's type parameter list here is a standard library forward iterator tag. And essentially what we're doing with this kind of whole block here through this inheritance scheme is we're saying that the type of iterator that we're creating is going to be a forward iterator. This is not going to be bidirectional. We're simply going to implement that bare bone set of iterator operations. So increment, dereference, as well as tests of equality. And the reason why we need to structure this class in this manner using this inheritance mechanism is many of the STL algorithms accept iterators of only a specific type. If we wanted to use find with, say, two of our doubly linked list iterator objects, if we just pass one in, find would not know if our doubly linked list iterator supported kind of the iterator functionality. And because it is inheriting the interface of standard library iterator of type forward iterator, the algorithm would know that this is a suitable iterator to go ahead and use in this finding process of some element within this sequence defined by the first iterator and the second iterator passed to it. So let's go ahead and continue on this journey. That's all I want to say about right now. These are traits. We're not going to get into that necessarily in this class. But this is an important component of our class definition if we would like to be able to pass these iterators to standard template library algorithms that allow us, that can be invoked with iterators that operate in the forward direction. Okay, so moving right along here, we're going to provide a default constructor for objects of the instantiated for our instantiated doubly linked list iterator objects. It's going to simply assign to current the null pointer. Okay. Next, we're going to go ahead and declare and define, just all in line within this class definition to keep things simple, a parameterized constructor, which will take a pointer to an object of a node of type T. And we're simply going to use whatever value is stored within that parameter to initialize current. So we'll see this is going to be one of the ways where we can define where our iterator is going to begin pointing to, and then subsequently we'll be able to move that iterator forward from that location, as well as dereference it to get the data in a particular node, or check to see whether or not two iterators are pointing to the same thing. So first operation here that we're going to define is the dereference operation for iterator type. If we go ahead and look here, it's the asterisk operator here. And if we notice, it's returning a reference to some sort of object of type T. What is it? What do we return in this case? Well, if we have an iterator to maybe this node within some sort of sequence of nodes in our linked list, remember the iterator is not going to return that node. Instead, it's going to return the data contained within our node. So iterators are interested in our data, not the underlying structure that houses our data. So in this case, our dereference operator is simply going to return currents data, which in this case is 10. We're then going to implement a test of equality. Are two iterators pointing to the same object? Well, in that case, we're going to go ahead and define this. It's going to return a Boolean value. It will have a parameter of type DoublyLinkedListIterator T. We're going to pass this by reference to const. We'll go ahead and name the parameter other, and we're simply going to return whether the address stored in the left-hand side's current is equal to that in that iterator presenting on the right-hand side of this operator. So if we had two doubly linked list iterators, let's call it DLLL1 equal DLLL2. That data members, or excuse me, that function member is going to be invoked, and the right-hand side is going to get bound to the other parameter, and then we'll go ahead and check to see whether that object's current is the same as that presenting on the left-hand side, which invoked that operator. Because remember, this is equivalent to writing this. And because this object invoked the operator, any mentions to functions, member functions by name, or data members is going to resolve to that object, the object who invoked the method. Okay, we're going to go ahead and define inequality. This looks very similar to our equality operator, except in this case, we're providing the definition of the inequality operator. So what's being returned? Well, a Boolean describing whether or not two objects are considered not equal. True if they are indeed not equal, false otherwise. We can see here that we're going to have a parameter, single parameter, other, passed by reference to const. It's going to be of type doubly linked list iterator T. And then we're going to see here that we're simply returning the result of the equality operator negated. So in that case, if our equality definition returns true, we know that the two objects are going to be not equal, or sorry, are going to be equal, meaning not equal should break. So inequality should return false. Okay, now here's the two, I guess, more fun ones, which are going to govern the traversal. So moving the one iterator to the next element within the sequence. We're going to do this, define it in two ways. We're going to do both the prefix and the postfix increment operators. And I'm going to go ahead and define these outside the class because they're a little bit more involved. So the first one up here is going to be prefix. So if we had, say, some doubly linked list iterator, doubly linked list iterator I don't know, for an int, call it iter. The definition we're providing right now is prefix increment. So that looks like that, where the operator is on the left side of the object invoking it. So in this case, we're first going to ensure that this object is not storing the null pointer because we're unable to reference the null pointer, or excuse me, dereference the null pointer. If this is true, we'll go ahead and set current equal to current next, and then we'll go ahead and return that iterator. So before we move forward, I want to go ahead and make it clear kind of the difference between a prefix and postfix increment. So if I have something like int i's initialized with 8, and I write std cout prefix increment I, I'm going to observe 9 written out to standard output. And then if I go ahead and simply output the contents of I again, we're going to observe 9. Now compare this with postfix increment. Go ahead and write int I is equal to 8, and then write std cout postfix increment I. We're going to observe 8. And then the second time, rather, if we were to ask what the value of I is thereafter, we would observe 9. So in the case of postfix increment, what's happening is the value is actually being incremented, but some sort of temporary of the previous state is returned. So the old result is used in the expression as we saw here. So the old result of I is written to standard output. However, each subsequent interaction with I would indeed reflect the incremented value. So postfix, think I'm going ahead, I'm going to perform the increment kind of after the operation has taken place. Prefix, we're going to increment and then use the value in the operation as seen here. With prefix increment on I, we see that I is incremented, and the result of that incrementation is used in the expression, which is why we observe 9 in standard output. And if we go ahead and look at that, say a second time, just asking, hey, I, what's your value? Of course, it was going to be what you'd expect, the integer value of 9. So with that in mind, in order to implement postfix increment, which we're doing here, we're going to need some sort of temporary so that we can perform the incrementation and then return the previous result. So as we get into the definition of this, the first thing we're going to do is create a clone of our iterator. So we're going to go ahead and pass to the copy constructor just the iterator that currently invoked this function. So that will be a brand new iterator implemented, constructed with the same, so clones current will have the same address as the iterator that we invoked plus plus on postfix. And then what's going to happen is now we're back to the iterator that invoked this function. We check its value of current. If it's anything other than the null pointer, we'll go ahead and move to the next element in the sequence, but we're going to go ahead and return that clone so that we have this behavior here, where the iterator is indeed moved to the next location. However, what is returned is going to be an iterator that would allow us to access the previous result. So if we look here, I++, in order for this to work, the old result has to be returned. However, the actual change to the object is reflected in any subsequent expressions as shown here. It's the exact same behavior that we have defined within the postfix increment operator for our doubly linked list iterator. Okay, with all that in mind, let's go ahead and move into, well, what updates do we need to make to our doubly linked list type in order to leverage the doubly linked list iterators that we have just defined.